So, welcome back again in this lecture. So, in the last lecture, we left with this slide, okay, in which we were looking at the choice of material for ICs. So, in the last lecture, as we have already discussed, there are so many materials. Basically, we are having certain elemental semiconductors like silicon, we are having germanium, we are having so many compound semiconductors, okay, that can be used for fabricating the IC, right? But the problem was why we have gone for the silicon. Okay, silicon is actually the most of the prominent material that we are actually using nowadays for manufacturing the IC. So I already told you about this, that the 95% of the semiconductor materials that we are using for making any devices, okay, is actually our silicon material. Okay, we are using the silicon as the material which is actually used for making almost every devices. Okay, and I already explained you different properties of this particular silicon material, why they are so famous. Okay, so certain favorable properties are there of the semiconductor silicon, which is it actually pauses, and because of that it is made possible that we are using the silicon other than the germanium or some other materials. So basically, if you see, the silicon is very abundant in nature. Okay, it is representing 25.7% of the earth's dust. I already told you about its process of refining is simple. Okay, and we will go through what process we have to follow to refine this silicon. Okay, because silicon is present in the environment or nature as a SiO2, okay, which is called as the quartzite. Fine, so it will be available in the form of quartzite, and then from the quartzite we have to do the refining process. So that refining process is simple. And I also discuss about the single silicon crystal. Okay, so growth of very high quality of single silicon crystal is possible. So it is not meaning that the only silicon single crystal is possible. Okay, we can also make germanium single crystal. So germanium single crystal growth is also possible. Fine. So you do not be trapped in this particular point that the single silicon crystal of high quality for silicon is only possible. Okay, so we can also make single silicon crystal of high quality for germanium also. Then I told you the basic reason that we actually that lead to uh, another major breakthrough is uh, this planar process. I told you about this planar process. Okay, so I have not explained this planar process, and today we have to look at what is the planar process. Okay, and planar process, what is this planar process and how it leads to a major breakthrough for IC fabrication, that we have to look at and we have to understand. Okay, so in the last class I told you about the single silicon crystal. Okay, so I told you that I will explain you what is single silicon crystal and what is polycrystal in silicon. Okay, so that we need to see. Okay, I have already explained you about the single crystals provide uniform and reproducible device characteristics. Okay, and thus provide the ability to integrate millions of identical components side by side on a chip. Now what we have to look at is, first of all, I have to explain what is the single silicon crystal, because this term is actually come up in this slide. So I will explain you first what is single silicon crystal, so that you will be able to differentiate between the single silicon crystal and the polycrystalline silicon. Fine, then I will be letting you know what is the planar process at this moment, because this discussion is very important. Fine. So just we move to the next slide. So our next slide is about types of solids. Okay. So this is a very basic slide you can find in any of the physics book. Okay. that if we talk about the solids, okay, this can be divided into three different categories, okay. And you might have come across these words like amorphous, like polycrystalline, like a single crystal, okay. So basically in amorphous, you know that if we are having any material, then these materials should be actually, it consists of a particular arrangement of atoms, okay. And if there is a certain arrangement of the atoms does not persist, okay, fine. In this case of amorphous, you can see that there is no certain arrangement of the atoms. These atoms are actually randomly distributed, fine. So if we have such distribution of the atoms, atoms are the smallest entity, though we are not talking about electron, proton, okay, and the other charged particles. They are the smallest entity we say, but atom is also a smallest entity that we have, okay. So these smallest entity that we are talking about, the atoms. So atoms are not arranged properly. They do not have any particular structure, fine. And therefore this structure is known as the amorphous structure, okay. It is amorphous. Now we can see in the polycrystalline the structure of these atoms, okay. The arrangement of these atoms are actually having a particular uh, periodic arrangement, okay. You will find that this atoms is having a regular structure. It is having certain ordered structure, okay. And that structure will be keep on repeating after certain distances, okay. It will be keep on repeating. So we can find that these atoms are actually having a particular ordered arrangement, fine. Now you can look at in the case of polycrystalline, right? When we talking about the polycrystalline material, what you can see is this arrangement of the atoms, fine. This arrangement of the atoms are actually you can see it is not repeating for the throughout the crystal, okay. We have a bulk crystal, and in the bulk crystal it will be occupying a large space, okay, large volume it will be occupying. And within this volume, the entire volume does not contain the same periodic ordered arrangement, okay. So what we can see, up to a certain volume or up to a certain distances, okay, a particular periodic arrangement is there, and then again a different arrangement of the atom is present, fine. A different arrangement of the atom is present. Similarly, you can see here again we have a different arrangement of the atoms, okay. So what we can see, when we are having a different type of arrangements within the material, right, in that case what we can say, it is a crystalline structure. It is not an amorphous structure, it is a crystalline structure. But this crystalline structure does not have only one ordered periodic arrangement. It is having multiple, the poly meaning is it is having multiple uh, ordered periodic arrangements, okay. So that's why we are saying it is a polycrystalline in nature, okay. It does have the particular arrangement of the atoms, which is an ordered and periodic structure, but this structure is not common for entire volume. It is actually containing large number of different ordered arrangements, and that's why we are calling them as a polycrystalline, fine. Now you can see when we are having a polycrystalline structure like this, then one of the periodic arrangement is separated by another periodic arrangement, and these are the called as the grain boundaries, okay. If you go through the different physics book, you will find that one terminology which is called as the grain boundaries, okay. So these grain boundaries are nothing but it is something imaginary boundaries, okay, that will actually separate one periodic arrangement from the other, fine. And we are saying that they are the periodic they are the grain boundaries. So basically what happens when these periodic arrangement within the material changes, fine. In that time, what you can see, because of the variation of the periodic arrangement, the electrical characteristics or electrical properties within this region and within this region will be a little bit different. Okay, it cannot have the same electrical characteristics, fine. And that if okay, so this is one of the things that you have to note down, that the electrical properties when we are changing from one grain boundary to the another grain boundary, like here and like here, and if you go to this side, okay, here it is like not a periodic structure, so I'm not talking about this, fine. I have taken this picture from the Google, I have not drawn it, fine. So these are the periodic, but this is not a periodic structures. Generally in the polycrystalline structure, all the structure should be periodic. Okay, normally it is a periodic structures, fine. So it should not be like an amorphous structure. Okay, so if you compare your polycrystalline structure with the single crystal structure, so in the single crystal structure, okay, you can see that the same periodic arrangement or the ordered arrangement of the atom is keep repeating throughout the material. Okay, in the entire material you will find the same periodic arrangement, fine. There is no any other arrangement will be found. So when we say it is a bulk material, so we are talking about a material or solid material whose dimensions is large. We are not talking about a very small dimensions material. It is volume will be large. Okay. And in that large volume, you will find everywhere it is having the same arrangement of the atoms. So what does it mean? If we having a polycrystalline bulk material and if we are having a single crystal bulk material, then we can see in the single crystal, because of the uh, constant periodic arrangement of the atoms, it possesses a constant electrical property. Okay, it will always have the constant electrical property within the material, everywhere it is same. But in the case of polycrystalline, the same property cannot be repeated when we are changing the grain boundaries. So in this grain boundary, in at this region, there will be a certain changes in the electrical property. So now from this discussion, okay, what we can understand, if we have a polycrystalline silicon, for example, because what I am saying that the silicon is one of the most prominent material that we are using nowadays for many for making ICs. Okay, then if we have a polycrystalline silicon, then you can understand here that if we have a polycrystalline, then if some devices are manufactured in one of the region and the other IC is manufactured in the other region, okay, or if some ICs are actually manufactured sharing this two particular different arrangements of the atoms, then you can see we have to make a very large number of like MOSFET or transistors within the chip, and those all MOSFETs or transistor will not be identical, as their electrical properties will be different. Okay, and that's why it is needed to have a single crystal of silicon. Okay, so that if we have a single crystal, if we make any MOSFET, any transistor throughout the material, then all the MOSFETs or transistors will have or will possess the same characteristics. Okay, it will not have the different characteristics, because we want to make identical transistors. We do not want to make a transistor which is having a different properties. Okay, we want to make an identical ICs, identical MOSFETs. So that's why what we have said in the last slide, you can see, we have said single crystal provides uniform and reproducible device characteristics, fine, and thus provide the ability to integrate millions of identical components side by side on chip. So this is very important thing that we need to understand why we are going for single silicon crystal. Okay, we are not manufacturing on polysilicon crystal. So this is one of the reason, and one of the advantage that you need to keep in mind. Now, if you understood these things, okay, because this terminology come up in our discussion, that's why I discussed this single crystal, okay. So now we can move on to the next thing that related to your planar process, okay. And before starting the planar process, I would like to give you more discussion, okay, and that discussion is related to what was the technique that we were using, okay, early 1950s for making transistor, okay. As we already know that I told you that the first transistor was actually invented in year of 1947, and that time the transistor were made on germanium slice, okay. And that time what kind of technique they were using that lead to the manufacturing of the IC, okay. So basically here I will tell you there are certain techniques that in the early 1950s they were using for making transistor. So one of the technique name was grown junction technique, okay. So we had one technique which is called as the grown junction technique, okay. So in this particular technique, whatever I'm going to discuss you now, you may be not comfortable little bit, uh, so you just try to just understand the things that I want to tell you, okay. You don't think like how these things have been done, because at present I have not discussed you how this silicon is actually the purification of the silicon is done, how the crystal is growing, okay. So those things I will be discussing in detail in the later slides, okay. But before that, because I want to explain you what is the planar technique and how this planar technique is the major thing or the major breakthrough that we got in somewhere around in the 1957 or 58, so that the only silicon is the choice and for making IC, and it replaced germanium completely, okay. Why it has happened, okay. So that we need to understand, because we also had the germanium as the choice of the electronic as the choice of the material, like as a choice of material, germanium we could have also used for making the transistor. But why we have not used the germanium and why we have gone for means silicon, so that we need to understand. So first of all, you just try to understand. So in the early times what they used to do is there were one technique which is called as the grown junction technique, okay. So first of all what they used to do is they were using, and they what they do is they first try to grow one of the single silicon crystal they used to grow. How it was grow, that does not matter at this moment, please note it down, okay. You do not bother about, I will discuss it later on, okay. So for the time being you try to understand, somehow they used to grow single crystal of the silicon, okay. Either it is single crystal of the silicon or it can be a single crystal of germanium, okay. So they used to grow the single crystal of silicon or germanium, and they try to add a particular dopant. So let us say our purpose is to make the NPN transistor, okay. We want to make an NPN transistor. So in the NPN transistor, we have the N layer, we have P layer, and again we have the N layer. So what they used to do is they used to grow the crystal, single crystal, and they used to add the impurity. Okay. So they used to add the impurity N type, then P type, and then again N type. Okay. So how they have done this, okay, how this crystal is grown, how this impurity was added, I will explain you when I will be discussing you about the Czochralski process, okay, which is used for growth of single silicon crystal, germanium crystal also, okay. So you do not bother about it, okay. So let us say this is this particular crystal that we have, and we have already added the N type dopant, we have added the P type dopant, and then again we have added the N type dopant. Now what we have to do is, because this thickness of the P is okay, okay, that was controlled during the doping process, okay, and during the growth of the crystal also, Okay, so this thickness was controlled, and these thickness are very high, you can see. So what we can do is we can cut this into a particular dimension. Okay, the thickness that we want. So that process is called as like sawing. Okay, sawing process. Okay, so we can cut this and then we can get this type of structure. So you can see we are having this n type layer, the middle one is the p type, and again the n type layer. You can see we have to cut this layer. Okay, so it is like something like a cylindrical shape. Okay, we have a cylindrical shape, then we can cut it from the bottom and also from the top. Okay, and then we can get this type of structure. Now you can see what we can do. We can further cut this particular slice. So we have already cut them into this slice, and then we can further cut into these type of slices. Okay, we can cut like this, we can cut like this, we can cut. There is a vertical cut, you can see, and then again we can have the horizontal cut. So if we do that, then you can see we can get a large number of identical NPN junction transistors. Okay, we can get the large number of identical NPN junction transistors. Okay, so what we have to do is now, if we cut, then we can get NPN type of transistors. Okay, so the middle portion is the P, the bottom one is the N, and the top one is again the N. And then we have to make a lead connections. Okay, so we make a lead connections by depositing a particular materials. Okay, so that material will be depending on which particular material we have used for manufacturing the transistor. For example, if we have taken the silicon, then generally when we use silicon, we are trying to grow the NPN transistor. We do not go for the PNP transistor growth. So we generally go for NPN transistor. And then we have to choose a material that will be making a ohmic contact with these layers. Fine. So because you are studying the VLSI technology, okay, I suppose that you must have studied about means in the electronic devices, that what is the rectifying contact and what is the ohmic contact. Okay, so we need to deposit such material, like when we are having a P type material. Fine, P-type layer, then generally the P-type layer, if we deposit a aluminium, then the P-type material, like silicon doped with the P-type dopant, if we deposit aluminium, then it will be forming a ohmic contacts. Okay, so we need to form a ohmic contact, and then we have to take out the leads. Fine, and this lead will be used for making the connections. As you already know that one of them is we can say, if it is a transistor like bipolar junction transistor, one terminal must be called as the emitter, then the base and the collector. And so you can see in this way we can have a large number of transistors that we can grow by the grown junction technique. Okay, so how it is, so this technique name is grown junction technique. So first we need to grow the crystal, and during the growth of the crystal we need to add the impurities. Fine, so this was one of the technique that they were using in the early 1950s. Right, now we have to look at the another technique that they were using, which is called as the alloy junction technique. Okay, so in the alloy junction technique, okay, so in the alloy junction technique, what they used to do is they used to get this type of substrate first. Okay, so getting a substrate is not a big task. So first they get a particular single crystal, and they will dope it with the particular dopant. Okay, so first we have to dope it, and then for making an structure, okay, like NPN structure or PNP structure. Okay, so what they do is they are placing a suitable dopant. Okay, like in this case what we have done is we have already taken a particular material, like it may be a silicon, it may be a germanium. So let us say if it is germanium, then we have already doped it with the some dopant materials. Okay, so you know that the dopant, like it could be an acceptor, okay, it can be a donor. Okay, So that you need to, I think you already aware of that. So we can make it as N type or P type. So N type dopants or P type dopants can be added. So now if we have this N type, then we have to make it P type, and then again we have to make a P type layer. So in the alloy junction technique, what we do is we are adding a suitable material. Okay, so first we need to put an indium layer at the bottom and then the indium layer at the top, and then we need to heat this complete structure. Okay, so when we heat this complete structure, then after means when this temperature is appreciably high, so that this indium will start melting. Okay, and when it will start melting, it will start diffusing, and it will start means it will start mixing to this particular material. Fine. So it will get mixed with it, and then it will be forming this type of a structure after the melting. Fine. So it will melt down and it will be forming this type of a structure. So now you can see this is your P type structure, this is N type structure, and this is your P type structure. And then we can again make the connections. Okay, we can make the connections from this terminal, from this terminal. Okay, and again from this N we can make another terminal. Okay, and this is the technique that is which is called as the alloy junction technique. Okay, I have taken these two pictures from the JD Planer's book. It is available in the page number 8 and 9. Fine. So this was the these were the two basic techniques: Rowan junction technique and alloy junction technique, that were used in the early 1952 early 1950s. Okay. Now we have to look at in the later years. Okay, in the same decade, somewhere around in the 1957 or 56. Okay, we had another technique. Okay, which is called as the double diffuse technique. Okay, so basically, in this technique, what they used to do is for making a transistor, they generally used to do these things. Okay, try to understand. So first of all, what they did is first they have taken a particular single crystal of material, whether it is germanium or silicon, and they doped it with a particular dopant. So let us say we are having a n doped single silicon crystal. Okay, then at that time, you remember they have invented one of the technique for adding the dopants. Okay, so the double diffuse technique, first of all, you need to understand uh, there were one technique which is called as the gas phase diffusion process. Okay, and it was actually invented at Bell Laboratory. Okay, so that invention lead them to have this particular double diffuse technique for making the transistor. So what they used to do, first they grow the crystal, single crystal, and while growing, they could add the impurity. So they added the impurity, and then what they did is they can have a source of p-type dopant. Okay, they will place this particular substrate, I will call it now as a substrate, which is the n-type doped substrate. Okay, so it is an n-type doped substrate. It may be a silicon, it may be germanium. So this substrate will be placed in a particular furnace, okay, in a particular chamber, in which we will be sending a particular dopant material, and it will be sent in the form of gas. Okay, and when we send this in the form of gas, it will have a particular diffusion constant. These materials will start diffusing to this top layer. Okay, it will start diffusing, and then it will go inside this material and it will form a particular layer of p-type materials. Okay, so it will have the p-type dopant at this region. Okay, so now you can see after the diffusion process of p-type dopant, we have done the means in this figure we can see we have already we have the p-type dopant sources, and then this p-type diffusion took place. Okay, gas phase diffusion took place, and therefore one layer of p-type material got developed over this particular n-type substrate. Now again we have to make which is called as another n layer we need, okay, because we want to make an NPN transistor, so we need to have another n type layer. Okay, so if we want to have another n type layer, then the same structure can be again exposed to a source which is containing n type domain. Okay, so again we have to send the gaseous phase of n type dopant, and then again a layer of n type dopant get diffused onto the top of this material, and it will again form a n type layer. Fine. So ultimately what we have is we are having a n type, p type and n type layers, and you will got this structure. Okay, so because we are doing this diffusion twice, okay, to grow the p type layer and again to grow the n type layer. Okay, so their technique was your gas phase diffusion technique. Okay, so that's why its name was derived as the double diffused technique. Fine. So this was the structure. Okay, this is the structure that you can get, NPN structure. And then you know that after getting this structure we need to make a connections. Okay, we have to make a leads. Okay, that will be connected to n, that should be connected to p, and that should be connected to n. Now you can see, because we need to connection from here, we need to make a connection from here. Okay, and then we have to also make the connection from the bottom. Okay, so either you try to make a connection from the bottom, or you can make the connection from the sides, or you can make the connection from the top itself. Okay, it will depend how you want to make your device. Fine, but we have to follow a certain rules. Okay, so let us say if you want to make a connection, how you will make this connection. Okay, obviously you can make a connection, right? We have to make a ohmic contact by depositing a certain material. Okay, that will be making an ohmic contact with the n type layer. You remember that this fact, that every material, okay, if you talk about lots of materials, okay, like we are having aluminum. So if we are having a different materials, all the material does not make ohmic contact, okay, with every layer like n type or p type, okay, or silicon or germanium. So basically we have to think of which particular material should be deposited if it is n type, which material should be deposited if it is p type. Okay, so that it will be making a ohmic contact. Okay, it should not be making a rectifying contact. Fine. So that we need to keep in mind, and we have to also keep in mind that whether we want to make rectifying contact deliberately or not. Okay, so basically the leads generally, but what we make is possessing a ohmic contact properties. Okay, so fine. So what we do is we need to deposit a certain material here, and from there we can make a lead. Okay, so let us say if we deposited a material here for making a contact. Okay, so this is actually connected with the n layer. Now you can see we have deposited a certain material which is not only connected with the n layer, but it is should be connected with the p type material. Okay, so how it will be done? Okay, then again we have to make a connection with this bottom layer also. Okay, so here just two layers or two connections have been shown, but that another connection we have to make. Okay, so what they generally do is they removing this side portions. Okay, a little side portions they remove. Okay, again a little portion they will remove from here, so that this n type layer and this p type layer should be localized. Okay, and you will find that this type of structure, okay, in the books you will find it is called as mesa transistor structures. Okay, in the mesa transistor, the mesa word meaning is that it is having certain a flat top, and there are steep edges. Okay, so that's why it is called as the mesa transistors. Okay, and this way they used to make the transistors. Fine. So now you can see they used to make the transistor, they used to make the contacts. Okay, like this. Okay, now the thing is that what you can understand is, you see, whatever be the junctions, okay, whatever be the junctions, if we cut this line from here to here, okay, you can see this, all the junctions are actually exposed, like all these junctions here, the lines are actually omitted, but these are the junctions here. Okay, junctions will be formed, and these junctions will be actually exposed to environment. Okay, these junctions will be exposed to environment. Fine. And these materials are nowhere isolated from the environment. Fine, everywhere you can see these junctions will be exposed to the environment. So this was one of the greatest disadvantage of having the double diffuse process. Okay, though it was better than the previous two technique, and they were used to make multiple devices on the same substrate, that you have to remember. Okay, they were used to make multiple devices on the same substrate, but it was also possessing a uh, disadvantage, and that disadvantage is that junctions were exposed to the environment. You remember that our junctions, our surfaces, our connections should not be exposed to the environment, because environment contaminate those junctions and the property of the devices will change. Okay, so that you have to remember. Fine. You can see the main disadvantage was that it had the exposed junction on the wafer surfaces and the edges. Okay, so this particular things were exposed to the environment. So this was the greatest disadvantage of this particular technique. Okay, so I hope you must have understood a little bit about how this fabrication where took place. They were used to make the transistors in the early 1950s and the late 1950s. Okay, now one of the major breakthrough that we have to discuss here, that actually changed the IC world. Okay, and that actually replaced the germanium material completely, and we have to be focused on the silicon only. Okay, so that we have to understand why the silicon is so much of means promising material, so much of prominent material, why everyone is now relying upon the silicon only. So that we need to understand. So this is due to the invention of the planar technique that you try to understand. Fine. So first of all, you see, this is the planar process that was invented by the Gene Horney, who was working at the Fairchild Semiconductors. Okay. This picture is again I have taken from the J.D. Plummer's book. Okay. So you can go through it. The page number I've already mentioned it. So now you can see what they used to do is, okay, what they used to do is they had taken a particular n-type substrate. Okay, then one of the major thing that he did in his invention was he was able to make a SiO2 layer on the top of this. Okay, he was used to make a SiO2 layer, okay, over the n-type substrate, whether it is n-type substrate or p-type substrate. Nowadays it is very common to fabricate SiO2 layers. Okay, so he was able to make a layer which is your SiO2 layer, and then he was again able to selectively remove a portion of the SiO2 layer. You just see in this picture. Fine. So he was able to remove selectively some of the portion of the SiO2 layer. Okay, and then what he could do is, what he did, so every step is actually not mentioned here in this graph, in this picture. Okay, not every steps are mentioned, there are lots of steps, and I will tell you when I will be dealing with the manufacturing process of your NMOS or PMOS transistors. Okay, so that time I will tell you in the detail. Okay, right now we just try to understand what is planar process. Okay, and what is the greatest thing about it. Okay, so you can see he was able to develop a SiO2 layer, and then he was able to selectively remove the portion of the SiO2. Then after removing this SiO2 layer, you already know that in the double diffusion process, we already invented the gaseous diffusion. Fine. So now what we can do is we can place this particular substrate along with this structure. Okay. with this particular window which is opened here, and then we can pass a certain dopants. We can pass a certain dopants in the gaseous form, so that only this portion will allow the diffusion of the dopants. Okay, and here these regions of the SiO2 layer will be acting as a mask for any kind of dopants. Fine. So what they will do is, what they have done, they passes the p-type dopants from here. Okay, and therefore they develop this particular p-type region under this window. Okay, it will be extending up to this, and it is taking this type of shape. Okay, so it has taken this type of shape, you can see. So it has extended a little bit inside, because the diffusion process, when the gas start diffusing, it will not only go vertically down, but it will also go to horizontal direction. So it is going like this, and then it is diffused in this fashion. Okay, so the p-type dopants got diffused in this region like this. Okay, and then what we can do is, we can again grow the SiO2 layer. Okay, so we can grow again an SiO2 layer, and then what we can do again, we can selectively remove a portion, okay, where we want to do another diffusion process. So you can see we have removed this small portion of the SiO2, selectively we have removed, and then again we have exposed it with the n-type gaseous phase dopant. Okay, and now this n-type diffusant got diffused, and we can got this type of layer of the n-type material. So now you have to appreciate one thing here is, you can see what we can do here is, due to this particular SiO2 layer, okay, what we can see is, we are able to select a certain region within the substrate where we can selectively do the diffusion process. Fine, as we have done the diffusion process up to this region. Okay, if you compare from the previous slide, this diffusion was done and the entire surface become p-type. Okay, you can see the entire surface become p-type, and there were no selective diffusion process. Fine, but in this case you can see we have done the selective diffusion, and because of this only this much of region becomes p-type. Similarly, because of this selective diffusion, this much of the portion becomes n-type. Fine, now what we can do, is we can make the connections, right? If we want to make a lead for making the connections, right, we can selectively remove this portion. I can deposit a certain metal at this point, and I can make a connection. Fine, so I can make a connection, right? Again, if I want to make a connection for this p layer, I can remove a certain portion from this, and then again I can make a connection. I will deposit a material, I will make a connection. Again, I want to make a connection for this n layer, I can remove it, and then again I can make a connection. Fine. So now you try to understand in the planar process. Okay, in the planar process, we are having a layer of SiO2, and the greatest advantage of this SiO2 layer is that it will be acting as a mask. Okay, it was able to oxidize the Si to produce the stable SiO2 layer. Okay, he was able to produce a stable SiO2 layer. Okay, and this SiO2 layer can be removed selectively. Fine, and this particular thing is called as the patterning. In the terminology of the VLSI, I will tell you in the detail. It is called as the patterning. We are developing a pattern. Okay, so we have developed a pattern in the SiO2 layer, and the same pattern can be transferred to the substrate. Fine, so this is called as the pattern. So now you try to say this. So what I'm saying here is, you can understand. So we are having the SiO2 layer, we can selectively remove it, and then we can do the doping process. Then again we can grow the SiO2 layer. Again we can selectively remove a portion and we can again do the doping process. And then we can have this type of structure of NPN. Now we can selectively remove it. We can make the connections. Fine. So now you can see everywhere, okay, everywhere what we can have is these layers are actually, all the layers are actually, it is covered with the SiO2. Okay, we just make a window, we will make a connection, but the other junctions area will be completely covered by the SiO2 layer. Okay, and this will this will prevent the junctions to be contaminated by the environment. Fine. So this is one of the greatest advantage that lead. Uh, there is a huge change uh, in the scientist minds, that what they thought, because the SiO2 layer is the only layer which is possessing this masking property. Okay, it is becoming a mask. So what you can say is SiO2 layer act as a mask for dopants, and therefore selective diffusion became possible. Okay, so germanium oxide, if you talk about can we grow a germanium oxide, the answer is yes, but the germanium oxide is not stable. Okay, germanium oxide is not as stable. What does it mean by the stable layer? That will be, I will be talking about it when I will be talking in detail about the fabrication steps, because there are certain temperatures that we need to discuss about it, and up to that temperature we need to heat this particular entire structure. Okay, and that time this layer should not be like removed or get vaporized, it should be stably present there. Okay, so that's why we are saying it is making a very stable SiO2 layer which is acting like a mask. And then this SiO2 layer is also providing the electrical passivation to the junctions. Okay, so it is actually an insulator. SiO2 will be acting like an insulator. Okay, so it will be used as a passivation layer. So basically what we can do, we can grow the SiO2 layer to completely cover this particular silicon. Okay, because even if we grow the SiO2 layer, the electrical property at the junction or the surfaces will never changes. This is one of the greatest property of the SiO2 layer. Okay, it will never change, and that's why this SiO2 layer provides electrical passivation to the junctions, and it is very much advantageous. Fine. So what I said is the growth of the SiO2 layer, and along with the patterning. Okay, this selective removal is called as the patterning. Okay, so you can see the patterning is the selective removal, and you will find in the case of VLSI, most of the time you will come across the word which is called as etching. The selective removal of SiO2 layer is called as the etching process. Not only SiO2 layer, some other layers also it is called as the etching process. Okay, so you must remember this terminology, etching process. So this is what we have, which is called as the planar process. Okay, in the planar process, SiO2 layer is having the greatest advantage of having masking property for the dopants. Okay, and along with the patterning process, okay, it is providing one of the greatest thing that leads to manufacturing of similar components like MOSFET, multiple MOSFETs, millions of means components that we are making on a particular same substrate. Okay, so we will stop here for today's discussion. Okay, we will be continuing in the next lecture. Thank you.